All right, in the previous video, we did critical points. In other words, all the values that have horizontal tangent lines. And I'm here to reassure your anxiety. We're only going to be caring about the x values today, even though if you wanted to figure out the exact coordinates of the point, you would solve for the x value of the critical point and then plug it back into f of x. So in today's video, the goal is, well, you know how to find critical points, but without actually graphing it, how can you tell based on the equation whether your critical point is a local minimum, in other words, a low point, or a local maximum, or a high point? And notice I'm saying a high point, a low point, as opposed to the lowest point or the highest point. In other words, where is the horizontal line equal to 0, and how can you tell whether it's a local maximum or a local minimum? Okay, so recall the steps. You have a function f of x. You basically want to set f prime of x equal to 0 and solve for x. You're trying to find the x values that have horizontal tangent lines. And then once you figure out which x values have horizontal tangent lines, you try to plug it back into f of x. That's how you find the coordinates. Don't worry about that today. I care more about, and most of the time in college, you care about what are the x values of the critical points. Are they a local minimum or are they a local maximum? So let's get on with the unit. Okay, so let's think. There's two methods. Today we're going to be focusing on the first method. That's what they teach you in college. The first method is what's called the first derivative test. The other method is called the second derivative test. So today is going to be on the first derivative test. Okay, let's get on with it. So basically, there's all this fancy lingo with, Greek letters and all that fun stuff. The first derivative test to me basically says, okay, let's use common sense about tangent lines before and after our critical point. So, for instance, I drew this. This is obviously a curve where the critical point is a local minimum. Okay, let me get my pen. So if I were to draw a tangent line before the critical point, so first things first, at the critical point, f prime of x is equal to 0. Let's just get on with it. So f prime of x is equal to 0 at this point right here. It's horizontal, it's a low point. But before the critical point, how would you describe this slope? Positive or negative? F prime of x is negative. That. Let me get back on the note. There we go. F prime of x is negative. Okay? Then the critical point has a horizontal tangent line, and then what happens to the curve? What is the tangent line, positive or negative? It starts to rise. So that tangent line is positive. So f prime of x is positive. So if you have a critical point, in other words, f prime of x is equal to 0, I'm going to look to the left, I'm going to look to the right. If before the critical point f prime of x is negative, and after the critical point f prime of x is positive, these are the characteristics of a local minimum. Because the slope is negative on the left, positive on the right, and f prime of x is 0 at the critical point, obviously. Okay, now let's take a look at this one. Well, let's get the obvious part out of the way. At the critical point, by definition, the slope of the tangent line is horizontal. Therefore, f prime of x is equal to 0. Let's picture this like you're throwing a baseball in the air. So I throw the ball upward. Let's say I'm right here and I'm trying to throw the baseball back into the infield. I'm in the outfield. I throw it back into the infield. So if I throw the ball up in the air, what happens once I release the ball? Before my critical point, what is the slope when I throw the ball up in the air? Positive or negative? So the ball, once I throw it, it goes up and it will hopefully, if I'm a good outfielder, Before the critical point, f prime of x is positive. Sorry about the blurriness. Yeah, but before the critical point, f prime of x is positive. Let me make that a little bit darker. There we go. So f prime of x is positive before the critical point. Then, there we go, green. After it reaches its highest point at that critical point, or a high point, then gravity starts to win, and the ball comes downwards. So f prime of x is negative after my critical point. So my tangent line gets negative after this critical point. So if your point has a positive slope, zero slope, and then a negative slope, those are the characteristics of a local maximum. Rise, flatten out, fall. Fall, flatten out, rise, that's a minimum. Okay? All right, so let me put this out of the way, and let's do some problems. And again, these are going to be the same problems that we did in the previous videos, but now we're going to use the first derivative test. So remember when I first started introducing critical points that I went back to algebra and went back to parabolas. So the directions are going to say, okay, find the x value, just the x value. You don't need to plug it back into f of x. Find the x values of the critical points, and once you're done with that, tell me, is it a local minimum or a local maximum? So for problem number 1, f of x is equal to x squared plus 4x plus 5. So in other words, I want to figure out where is the critical point. So I'm going to set f prime of x of this quadratic trinomial. And the derivative of x squared is 2x. The derivative of positive 4x is positive 4. And the derivative of positive 5, well, that's a flat line, that's 0. So 2x plus 4, we set it equal to 0, and now we're trying to figure out which x values have a horizontal tangent line. So let's solve. 2x plus 4 is equal to 0 by subtracting 4 from both sides. Positive 4 minus 4 cancels out, and I'm left with 2x is equal to negative 4. And then I've got 2x is equal to negative 4, so I'm going to divide both sides by 2. So what this tells me is that the horizontal tangent is only at one place. X is equal to negative 2. And again, you would plug it back into f of x, and that's how you would figure out the y-coordinate of the critical point. Now, here comes the first derivative test. Okay, so basically what you would do is I like to go 1 to the left and 1 to the right. So one value to the left of negative 2, basically what you would do is take the derivative f prime of x is equal to 2x plus 4. And you would do f prime of negative 3. And then you would go one space to the right. F prime of one space to the right would be negative 1. And again, it doesn't have to be those values. It could be way to the left. It could be x equals negative 10 and x equals positive 5, something like that. But I like to go 1 to the left, 1 to the right. So 2 blank plus 4. Okay, so let's just go 1 to the left. F prime of negative 3. So then 2 times negative 3, the slope of the tangent line to the left of negative 2, that would be negative 6 plus 4. Negative 6 plus 4 is negative 2. I don't care so much about the number -2, but I do care, is this slope positive or negative? So before x equals -2, the slope is negative. Okay? And then I'm going to go to the right, f prime of -1. 2 times -1 is -2, plus 4. -2 plus 4 is +2. And again, I know it seems like a coincidence that the slopes are 2 or -2, but care more about the signs. After the critical point x equals -2, is this slope positive or negative? So after x equals -2, our critical point, the slope is positive. So therefore, if the slope is negative, 0, and then positive, that tells me that this particular critical point is a local minimum. So x equals -2 is a local minimum. And I'm going to graph it. You know, again, I know I said I wasn't going to graph it, but I think that it really helps to see it as we check our algebra. Boom. At x equals -2, we have a negative slope, a 0 slope, and then a positive slope. So that x equals -2 needs to be a local minimum. Okay, so I'm going to get rid of it. Moving on to the next one, y equals x squared minus negative x squared plus 18x minus 75. Find the x values of the critical points and determine whether the critical point is a local min or a local max based on the first derivative test. Sorry, I needed a sip of water. So basically what you need to do is find the critical point. Well, you would take f prime of x, the derivative of negative x squared with respect to x would be -2x. Let me just scoot over because the shadow's in the way. There we go, much better. The derivative of negative x squared with respect to x is -2x. The derivative of positive 18x would be positive 18. Okay? And the derivative of -75, it's 0 because it's a constant. Set it equal to 0. Let's solve for x now. Let's set f prime of x equal to 0 and solve for x. So -2x plus 18 is equal to 0. I'm going to subtract 18 from both sides. So then -2x is equal to -18. And then I'm going to divide both sides of the equation by -2. So then x is equal to +9. That's an x value. That's a critical point. So that tells me that x equals 9. The slope of the tangent line is 0. Okay? So now I'm going to pick a value before and after this critical point. So let's say I pick before 9, that'd be 8, and after 9, let's just say 10. Again, because it's the only critical point, I could pick x equals 1, I could pick x equals -15, but I like 1 to the left, 1 to the right. So basically you go to f prime of x, right? So you're going to use f prime of x is equal to -2x plus 18, and I'm going to go f prime of 8. That's -2x plus 18. So then, -2 times 8 would be -16 plus 18. That would be positive. Again, it's back to 2, but the idea is, okay, this is a positive slope. So before the critical point, so before x equals 9, the slope is positive. So it's rising. Then x equals 9, the slope is horizontal. And then let's go barely to the right. There we go. Negative 2 times positive 10 would be negative 20. Plus 18, which is negative 2. So after my critical point, after x equals 9, my slope is negative. So if I analyze the situation, before my critical point, slope is positive. At my critical point, x is 0. After the critical point, x is equal to 9. So before, at, after, positive to 0 to negative. Those are the characteristics of a local maximum. Okay. All right. Moving on to problem number 3 now. F of x is equal to 2x squared. Oh, I forgot to graph it. Sorry. Now we're going to look at the graph. So just to confirm with the graph, this is what the graph looks like for y equals negative x squared plus 18x minus 75. The critical point is at x equals 9. Before the critical point, the graph is rising, flattens out, and then falls. Positive to 0 to negative are the characteristics of a local maxima. Maxima would be plural. All right, moving on to problem number 3 now. F of x is equal to 2x squared minus 8x plus 5. So you get the idea. You set f prime of x equal to 0. In this case, the derivative of 2x squared would be 4x. And then negative 8x, the derivative of that is minus 8. And that's equal to 0. Now that I got f prime of x equal to 0, I'm going to solve for x by adding 8 to both sides. So then I got 4x is equal to positive 8. Now I'm going to divide both sides of the equation by 4. And therefore, x is equal to positive 2 is where my critical point is. Okay. So I know what you're thinking. Like, go one to the left and one to the right, and it's going to be like some sort of so I'm gonna have a little fun. Actually, you know what? I can do one to the left and one to the right. So check this out. So suppose I do f prime of x is equal to 4x minus 8 on to the left and to the right of it. So one space to the left of 2 would be 1. And then one space to the right of 2 would be 3. 4 times 1 is 4. 4 times 1 and then minus 8. 4 minus 8. That'd be negative 4. So I don't care too much about the number, but I do care about the sign. Before my critical point, before x equals 2, the slope is negative. And then I go over here, 4 times 3 is 12, minus 8 is positive 4. I don't care too much about the number, but I do care that the slope after my critical point is positive. So if my graph goes negative to 0 to positive, then that tells me that this coordinate of the critical point is a local minimum. Okay. Now, x equals 2. Let me just take that off. X equals positive 2. Negative to 0 up is a local minimum. Okay. Let's take a look at this. F of x is equal to negative 2x squared minus 20x minus 46. So the same old, same old. I'm going to find f prime of x. I'm going to solve for the x values that make the horizontal tangent line. The derivative of negative 2x squared would be negative 4x. The derivative of negative 20x would be negative 20. And the derivative of negative 46 would be equal to 0. So now I'm going to solve for x. I'm going to add 20 on both sides, business as usual. So negative 4x is equal to 20. Then I'm going to divide both sides of the equation by negative 4. Cancel out. Therefore, my critical point lies at negative 5. So far, so good. So now I'm going to test it before x equals negative 5. My derivative formula is negative 4x minus 20. So now let's go one space to the left of negative 5. Let's go with x equals negative 6. And let's go one space to the right of negative 5. Let's go with negative 4. So negative 4 times negative 6 would be positive 24 minus 20. I don't care too much about the number, but I do care about the slope being positive 4 before my critical point. And then over here, negative 4 times negative 4 is positive 16 minus 20. I don't care too much about the number, but I do care about my slope being negative 4. So before my critical point, my slope was positive. Then at my critical point, it flattened out. And then it fell to negative. So this tells me that the critical point is a local maximum. And I'm going to graph it to show you. Go back home. So when x is equal to negative 5, that is the characteristic of a local maximum. Okay, moving on. Problem number 5. F of x is equal to x cubed minus 3x squared. So now we're in business. Specifically, f prime of x, since this is a cubic function, there's probably going to be more than one critical point. So let's take the derivative of x cubed. The derivative of x cubed is 3x squared. The derivative of negative 3x squared would be negative 6x. And we set it equal to 0 to find the horizontal tangent line. Okay, so now I'm going to solve for x by factoring out 3x. 3x times x is 3x squared. 3x times negative 2 is equal to 0. And I'm just going to skip the algebraic step since we did this in a previous video. So therefore, our critical points are located at x equals 0 and x equals positive 2. Now we've got two critical points. I am not looking forward to this. So let's think about this logically. So my plan is to test before and after 0. So I'm going to plan the first derivative test for f prime of negative 1, f prime of 1, and then, because these are horizontal, and then f prime of 3. Okay? So let's take a look at the f prime of x formula. That would be 3x squared minus 6 blank. Okay, and then So remember, at x equals 0, the slope of the tangent line is horizontal. At x equals 2, the slope of the tangent line is horizontal. And I'm going to test out whether what are the tangent lines before and after our critical points. So let's find f prime of -1. So that'd be 3 times -1 quantity squared. That'd be 3 times 1. And then -6 times -1 would be +6. 3 plus 6 is +9. So that tells me that the slope at x equals -1 would be positive. Okay? And then x equals 1. That'd be 3 times 1 squared. That'd be 3 times 1. Minus 6, or 3 minus 6. So when the slope is, when we try to figure out the slope at x equals 1, 3 minus 6, that'd be -3. So that tells me that at x equals 1, the slope is negative. Okay, so then I'm going to apply x equals +3, just barely to the right. So now we've got 3 times 3 squared, which would be 3 times 9, minus 18. 3 times 9 is 27, minus 18, and that would be +9. So at x equals 3, it's positive. So if I can just examine from left to right, so f prime of x is +0, -0, positive. So if it goes positive to 0 to negative, rise, stop, fall, that is a local max. If it goes from negative to 0 to rise, that is a local min. Okay, let me check with the graph. So if I take a look at this, let me make it a different color other than black just to distinguish it. Let's go with blue. There we go. So remember that our critical points are located at x equals 0 and x equals 2, like our work indicated. X equals 0 is a local max. X equals 2 is a local min. We have checked our work. I love calculus. It's poetry. Okay. So f of x is equal to 2x cubed plus 3x squared minus 12x. Find the x values that give me horizontal tangent lines and prove, are they a local min or a local max? Let's find out. So basically, let's do the same old song and dance. F prime of x is equal to the derivative of 2x cubed, which would be 6x squared. The derivative of positive 3x squared, which would be positive 6x. And the derivative of negative 12x, which would be negative 12. Now that we know that f prime of x is 6x squared plus 6x minus 12, let's set it equal to 0 and solve for all the values of x that satisfy the statement. So let's factor. Let's go back to algebra and factor. I'm going to factor out a 6, leaving me with x squared plus 1x minus 2 is equal to 0. Now that I've factored out the 6, we have to use our quadratic trinomials method, what two numbers multiply to -2 and add to +1. Well, that winning combination was +2, -1. So x plus 2, x minus 1 is our factored form of this quadratic trinomial. So therefore, our critical points are located at x equals -1 or x equals 1. So it might help to actually view this like a number line. So I care about -1 and I care about 1, And this is where f prime of x is equal to 0. And f prime of x is equal to 0. X equals -1, x equals 1. So I'm going to test somewhere over here. Test to the left of -1, test between -1 and 1, and test after x equals 1. So let's say I want to test f prime of -2. F prime, what's between -1 and 1? Well, 0. F prime of 0 and f prime of 2. Okay, so let's look at the derivative formula. That'd be 6x squared plus 6x minus 12. Let's see, what was that? Plus 6x minus 12. Okay, let's take a look at this. So if I'm going to test out x equals -2, here we go. -2 quantity squared is +4. So 6 times 4. +6 times -2 would be -12, and then -12. So 6 times 4. Hang on, did I do this right? -12. So that'd be 24. Oh, duh. I messed up. Let's go with -3. Why not? Let's go with -3. There we go. Sorry about that. So that would be 6 times 9 minus 18 minus 12. That'd be 54 minus 18 minus 12. So -18 plus -12, that'd be -30. Well, that would be +24. So what this means is that before, our slope is positive. In between -2 and 1, let's find out. Let's pick a value in between. Let's go with 0. Because I like x equals 0. Well, 6 times 0 squared plus 6 times 0 minus 12, that'd be -12. All I care about is between x equals -2 and x equals 1, our slope is negative. And then let's test out a value to the right of x equals 1. Let's go with x equals 2. So what this tells me is 6 times 2 squared, that would be 6 times 4, plus 6 times 2, which is 12, minus 12. Well, 12 minus 12 is 0, so this is going to be +24. So after our critical point, our slope is positive. So remember that at critical point x equals -2, it goes from positive to positive to 0 to negative. Rise, stop, fall. So those are the characteristics to me of a local maximum. Then, at x equals 1, the slope goes from -1 to 0 to rising again. Fall to stop to rise. Those are the characteristics of a local minima. And let's check with the graph. You zoom out. Ooh, yeah, so at x equals -2, that is a local max. At x equals 1, that is a local min. Okay, one more, and then we'll call it a day. So, f of x is equal to x to the 4th minus 2x squared. This one might take a while, so get a breather, pause the video if you need to. Let's get on with it. So f prime of x is equal to 4x cubed minus 4x is equal to 0. Let's do some factoring. 4x gets factored out. 4x times x squared, and then 4x minus 1, 4x times negative 1. So then we factor this into the difference of two squares, gets factored into conjugates, x plus 1, x minus 1. Long story short, my critical points are at x equals 0, x equals negative 1, and x equals 1. So now let's pretend I make a number line and I want to care about the slopes. So I've got 0, I've got negative 1, and I've got positive 1. So I can't really use a horizontal in between these. But basically what you want to do, so this is f prime of x equals 0, 0, 0. So let's calculate the behavior. So f prime of x is equal to 4x cubed minus 4x. So let's do that. 1, 2, 3, 4. 4 times. So if this is tedious, I'm glad, because the next video shows it much easier, I assure you. So let's pick a value to the left of negative 1. Let's go with negative 2. So that's going to be, I'm just going to jump right to it, negative 8. 4 times negative 8 plus 8. That's going to be negative 32 plus 8, or negative 24. So my slope before x equals negative 1 would be negative. Let's pick a number in between negative 1 and 0. Let's go with negative 0.5. So I get my calculator, negative 0.5 quantity cubed. That'd be negative 0.25. Well, I'm just going to eyeball this. And then half of negative 4, that'd be 0.5. But the idea is, if I were to multiply that by 4, I would get negative 0.5. Wait, hold on. Oh, wait, that's positive 2. I would get negative 0.5 plus 2, which would be 1.5, which would be positive. And then between x equals 0 and positive 1, so let's go with positive 0.5, just because. Boy, oh boy, I'm getting frustrated, and I have a math degree. But the next video will make it much clearer. So that's 4 times 0.125 minus 2. So that'd be 0.5 minus 2, which would be negative 1.5. But the real thing that I care about is that the slope between x equals 0 and x equals 1 is negative. And then let's hope that we can get a solid answer out of this. So this would be 4 times 8 minus 8. So that'd be 32 minus 8, which would be 24. So let's analyze this for the last time. Okay. Fall, 0, rise. That's the characteristic at x equals negative 1 to be a local minima. Rise, stop, fall. Rise, stop, fall. Those are the characteristics of being a local maxima. Fall, stop, rise. Fall, stop, rise. Those are the characteristics of a minima. So my local minima are at x equals -1 and x equals 1. And my local maximum, there's one of them, is at x equals 0. So just to graph this for the final time, put this graph up there. Look at that. Minima, minima, maxima. In the next video, take a deep breath. This was a long one, I agree. The next video is going to show the other method, which I'm a little biased, is a much better method. It's called the second derivative test. Have a good one.